Hello and welcome back to Double Award Physics, Electricity. This lesson is going to be about current voltage graphs. It'll be a short lesson, this one. It's just to explain the keys behind types of graphs. Okay, so this is our standard type of graph. We've got two axes, and on the y-axis is current I measured in amps, and across the x-axis we have voltage measured in volts. Okay, so V/V. Now, this is a little bit against what you expect to happen because it's current against voltage. It would be better if there were voltage against current, but the CCEA specification says you must know about IV graphs. Okay, so normally it will be current up the side and voltage across the bottom. Now, if I have a perfect ohmic conductor, that means it follows Ohm's law perfectly, then as I increase the voltage going this way, then the current traveling through it will also increase. Which kind of makes sense that if each coulomb of charge is getting a little bit more energy, then you can pack them through a bit faster. Okay, the gradient of this graph is 1 over the resistance, and that sounds a little bit mathematical, but we'll try and explain that in more simple terms. Just remember that the gradient, okay, how slopey the graph is equal to 1 over the resistance. Now basically this means that as it gets steeper, that means less resistance. Okay, and that's why I don't like these graphs, simply because of that. Okay, that's counterintuitive. That if something gets more and more steep, it becomes easier. Okay, but as this graph gets steeper, it becomes less resistive. Okay, so this line here that I've just drawn in, this is actually lower resistance. Okay, and that should go kind of, if you think about it, it's not too difficult if you read what's happening, that as each little coulomb of charge, whoopsie doodle, alright, let's try a better line, as each little coulomb of charge here is receiving less voltage, it's still got quite a high current, whereas for the same graph with the same voltage, it's actually got a much lower current. Okay, so even though these two lines have the same energy per coulomb, the amount of coulombs passing per second in the second graph is actually greater than the first graph. And if any of that made any sense to you, you're doing very well. Basically what you have to remember is that this is less resistance and this one is more resistance. Okay, if you've got that, you're doing very, very well. Okay. Now that is for a perfect ohmic conductor. Okay, so that's for a perfect resistor or for a perfect piece of wire. Okay, the real life world is not like that. No wire is perfectly ohmic, and that means that we have to discuss one different type of conductor. Okay, and this is a kind of key conductor that you'll see, well, probably not so much these days because we've all gone to energy saving versions, but this is the energy saving light bulb, or not the energy saving light bulb, the regular light bulb before it. Okay, so the regular light bulb, the filament light bulb, which is basically that you have a little evacuated glass area filled with particular gas, and you pass current through the wire. The wire gets hot. It glows so bright and so hot that it gives out white light. That's the basic principle of a lamp. The thing about a lamp is that the reason it gives out light is because it heats up. And heat is simply the movement of atoms, or movement of ions inside the metal. Okay, and they're bouncing around inside like mad. You remember our diagram last time. Okay, and essentially what happens is that if you have a voltage current graph, okay, so you have voltage across the bottom, again your current up the side, amps and volts, then at low temperatures or at low voltages and low currents, the graph's nice and ohmic, no bother at all there. But as the voltage gets greater and the current gets greater, what happens is it begins to trail off like this. Okay. I'm doing this with a mouse. Okay, this is supposed to be an actual smooth curve. Okay, but you get a curve. I'm going to try that one more time, a little bit more steeply. The curvy nature of it going on. That's the one. Okay, so you get a curved graph like this, and the reason you get a curve is that as the metal heats up, the ions inside are vibrating back and forth a lot, and they're causing more collisions for the little coulombs of charge that are coming through. As a result, it gets more resistive. Remember, as this graph levels off, there's more resistance. So here, in this little section my pen's at, not particularly resistive, it's going quite steep, no bother at all. And then it starts to get more resistive. At this point, it's starting to heat up quite significantly. It's probably starting to glow around here. And then as it begins to glow white hot and starts to give out light, the resistance becomes very, very, very great indeed. And you end up with a curve that eventually, basically levels off. That even though you're trying to bung more current through and you're trying to give each of the coulombs extra energy per coulomb, you're not affecting anything really. Okay, you're just driving more energy. Okay, so that's your IV graph for a filament bulb, and this is part of the course. This is a very, very important one. Okay, so this is an IV graph for a filament bulb. And just to make sure that we're not taking anything for granted, this little bit that's actually inside the light bulb, that's called a filament. Just a thin piece of metal, okay, that warms up and glows when you pass current through it. Okay, now because you can run electricity in two directions, you can run it either positively, so you can send your current forwards. You can send your current backwards through a circuit. So technically speaking, this graph has a mirror image as well. Never seen it asked, but you can have the opposite on the other end. It's a terrible reflection. Let's try that again. You can have the opposite the other way around. Okay, so it starts off going steeply downwards. We will get this. I hate my mouse. Steeply downwards, and then it begins to curve off. Okay, so you get a big elongated S shape that goes through the origin. Right, that'll do us for graphs today. Next time we'll maybe try and explain why heat causes energy loss, and we'll talk about the actual amount of energy. Stay tuned.